Electric field. Electric field. It is defined as the space around an electric charge. Electric field. It is defined as the space around an electric charge where the effect of the charge is felt is called as the electric field. So the place up to which the effect of the charge is felt. The effect of the charge means attractive force or repulsive force by another charge. So the area around a charge up to which extent its influence is felt is known as electric field. For example, in the figure, you notice a white circle around a red dot. That is known as, let us imagine, the electric field is situated like this. The radius of this circle can go on to increase up to infinity. So that is, theoretically speaking, it extends up to infinity from a point charge. Electric field is measured with a vector quantity known as electric field intensity, indicated with capital E bar. Electric field is measured with a vector quantity, electric field intensity E bar, and it is defined as the force experienced by unit positive charge placed at that point. The unit positive charge placed at a point experiences some force. That force experienced by unit positive charge is called as electric field intensity. On placing a test charge Q0, at point P, suppose the force experienced by it is, say, F bar, then the electric field strength, electric field intensity is given by E bar is equal to F bar by Q naught. F bar by Q naught. The direction of electric field strength, electric field intensity, is same as the direction of force experienced by this test charge. The direction in which the force is experienced by the test charge is same as the direction of the electric field. It is measured in newtons per coulombs or in volts per meter. It is measured as newtons per coulomb or volt per meter. Electric field line, it is already defined. It is an imaginary line. Physically they don't exist, but we imagine. If we imagine a test charge Q0 in an electric field, it experiences the force in a particular direction, or sometimes it moves along a particular direction. That direction along which it can travel is known as electric field line. The path followed by the test charge in an electric field is known as electric field line. We can imagine electric field lines about charges. Let us consider positive charge. Around this positive charge, if you imagine a test charge to be moving from different points around this test charge, point charge, then it moves along straight lines. If you imagine the space around this charge, then these lines, we can understand them as the radii of the sphere around this charge. So they along the radii and outwards. From the center of the sphere, these lines are situated out of the sphere. If you take a negative charge, the field lines will all converge to the center of the sphere. No doubt they will be situated, they will be lying along the radii and they will converge to the center of the charge sphere. So by a positive charge, the field created is diverging field. By a negative charge, it is a converging field. We represent diverging field by the vectors moving away, and if the vectors are coming towards a point, it is a converging field. We can also draw electric field due to 2 point charges. Let us consider 2 positive point charges. If 2 positive point charges are situated at some distance, then if you draw the electric field line, it will be as shown in the bottom figure. So like this we can represent electric field lines, electric field by electric field lines. We define uniform electric field as an electric field in which the magnitude is the same at all points and the direction of the field is the same at all points is termed as uniform electric field. In an electric field, if the direction is the same and the magnitude is the same at all points in an electric field, such an electric field is known as uniform electric field. It will be represented by parallel arrows. It will be represented by parallel lines with the same direction, arrows in the same direction. The electric field lines will be traveling from positive charge to negative charge. If there are 2 charges, one is positive, the other one is negative, the electric field lines will be situated from positive charge to the negative charge. So we can imagine on the left, where we notice parallel arrows. On the left, there will be positive charge. On the right, there will be negative charge. And it will be represented by parallel arrows, as shown above. A field in which neither the magnitude is the same nor the direction is the same, such a field, electric field, is known as non-uniform electric field. Non-uniform electric field. In the bottom figure, you notice 2 charges. One is positive, the other one is negative. Left one is positive, right one is negative. Such a pair of charges is known as dipole. A pair of positive and negative charges is known as, they are of same magnitude. If they are separated by some distance, they are called a dipole. Dipole means 2 poles. The electric field due to such a dipole is shown in the bottom figure. Here the field lines are starting from the positive charge and they are moving towards the negative charge. So the charges, the field lines, they start from positive charge and they end on negative charge. So dipole field will be as shown in the bottom figure. Now let us study some of the properties of field lines. Electric field lines. It is an imaginary line. It has no physical existence. It is the direction in which a positive charge moves. A uniform electric field is represented by equidistant parallel arrows, parallel lines. If the electric field is a curved line, then the field direction will be along the tangent at a point. At any point, if you want electric field direction, draw a tangent at that point. The tangent indicates the direction of electric field at that point. At any point, an electric field will have only one value, only one magnitude and one direction. So when we draw electric field lines, no 2 electric field lines will intersect. If they intersect at a point, that means the field has got 2 directions. It's not possible. The number of lines which are situated through unit area represents electric field strength. If the number of lines, crowded together, then the intensity, the electric field strength will be more. If they are separated, widely separated, the electric field strength will be less. Crowding depends on the strength of the electric field. The lines of force, they diverge from a positive charge and converge towards a negative charge. The field lines, they start from positive charge and end on negative charge. So we say they diverge from a positive point charge and they converge to a negative point charge. Now let us study some of the properties of field lines. Electric field lines. It is an imaginary line. It has no physical existence. It is the direction in which a positive charge moves. A uniform electric field is represented by equidistant parallel arrows, parallel lines. If the electric field is a curved line, then the field direction will be along the tangent at a point. At any point, if you want electric field direction, draw a tangent at that point. The tangent indicates the direction of electric field at that point. At any point, an electric field will have only one value, only one magnitude and one direction. So, when we draw electric field lines, no two electric field lines will intersect. If they intersect at a point, that means the field has got two directions. It's not possible. The number of lines which are situated through unit area represents electric field strength. If the number of lines, crowded together, then the intensity, the electric field strength will be more. If they are separated, widely separated, the electric field strength will be less. Crowding depends on the strength of the electric field. The lines of force, they diverge from a positive charge and converge towards a negative charge. The field lines, they start from positive charge and end on negative charge. So we say they diverge from a positive point charge and they converge to a negative point charge. Let us derive a relation for electric field strength. Let us derive a relation for electric field strength. Let us suppose the test charge Q0 is at a distance d from a point charge Q plus Q. Then a repulsive force exists between these two charges. We know from Coulomb's law, this repulsive force F is given by 1 by 4 pi epsilon naught Q0 by d square. The repulsive force between Q and Q naught is 1 by 4 pi epsilon naught Q naught by d square. This is repulsive because both charges are positive charges. The definition of electric field strength is force divided by test charge Q0. So, electric field strength E bar is equal to F bar by Q0, that is equal to 1 by 4 pi epsilon naught Q by d square. So, from a point charge at a distance d, electric field strength is given by 1 by 4 pi epsilon naught Q by d square. Here, the direction of field strength is away from the charge Q because it is a repulsive force. So, at Q0, the field will be away from Q. Now, we can consider as though the test charge Q0 is placed at a point in an electric field of strength E bar. The relation for force can be imagined like this. We can consider Q0 is placed in an electric field of strength E bar. So the relation for force can be written as F bar is equal to Q0 into E bar. This is the relation between charge, field strength and force. So if there is a charge Q0 in an electric field of strength E bar, then it experiences a force the force experienced by it is F bar is equal to Q naught E bar. Force on a point charge placed in an electric field. Let us consider uniform electric field of intensity E. In that electric field, suppose 2 point charges, one is positive, the other one is negative, are situated. Just now we have seen, if a charge Q is placed in an electric field of strength E, then it experiences a force, and that force is given by QE. If it is a positive charge, the direction of the force will be the direction of the field, and on negative charge, the direction of the force is opposite to the direction of the field. And we have derived the relation for electric field strength at a point as E bar is equal to 1 by 4 pi epsilon naught Q by D square. The electric field strength is 1 by 4 pi epsilon naught Q by D square. This is in vacuum or air. In a medium of permittivity epsilon, the electric field strength is 1 by 4 pi epsilon Q by D square. If the charge Q is situated in a medium of permittivity epsilon, then the force experienced, the field strength created, is 1 by 4 pi epsilon Q by D square. If you take the ratio of the field strength in air and in vacuum, in air and in medium, the field strength in medium is equal to the field strength in air by epsilon r, relative permittivity, because epsilon is equal to epsilon naught epsilon r. By substituting epsilon naught epsilon r for epsilon, we get the relation for electric field strength in a medium as epsilon r ER, field strength in air, by epsilon r. So this is the relation between field strength in a medium and in vacuum.